Hi all, this is Mr. Yeager. Today we are going to look at two topics very briefly. One is the idea of what is net force. Obviously this was introduced some in the last unit with equilibrium. During equilibrium we had net force always equal to zero, so what happens when it's not equal to zero? That's where we're hitting now with unit 3 with dynamic forces. And then 2, I'm going to quickly again go over the idea of the third law problems. What do we mean by Newton's third law? How does it work? Okay, how does it work? So, for net force, okay, the big thing with net force is you have the formula, net force equals m times a, m times a. And I know on your formula sheet, they have it written just slightly different. They like to write it as a equals the net force divided by m. It's the same thing, okay? It is the exact same thing. So, the issue is, net force is not just simply equal to ma. It's equal to the sum of the forces acting on the object in a particular direction. Okay? The sum of those forces acting on it. So what happens, what I usually see as we start working with this, for those that struggle with it, is when it says solve for net force, everybody only thinks ma, which that's good. That's good. That's absolutely correct. It is mass times acceleration, but they might not give you that information, and instead you need to look at the different forces acting on it. Okay? We have to understand, obviously, again, as we went over in the last unit, if the forces are acting together, if I have two force applied acting together, all right, these two get added together. That's the sum of the force. Okay, the net force on it is not just one or the other, it's both of them together. If you have those forces that are opposite of each other, okay, I'll do applied and friction, I need to subtract those forces. So we have to understand that these problems can be given lots and lots of different ways. You need to understand where to approach the problem and not be fixed on only one method working. One method, and obviously this class, as you already know, will not work. All right? You need to be prepared. You need to be prepared to be able to handle a problem for many, many approaches. So, I have a couple example problems we're going to do with net force quickly. Okay. Oh, my pen. Okay. So, well, let's do a couple problems briefly here. This won't take very long. So let's look at number one. You have a 50 Newton applied force is used to accelerate the object to the right across a frictional surface. The object encounters 10 newtons of friction. Use the diagram to determine the normal force, the net force, the mass, and the acceleration of the object. Neglect air resistance. Okay. So this is more of a regular physics type problem, but I mean, obviously the method we're going to use here will be done on every AP physics problem where you might just have to do an extra step. All right. So with net force on this one, we basically look at what we have. Okay. You can see a lot of information is already given to you. It has to be. Okay. And this is we're going to already say this is on a flat surface. Oops. Get a pen here. You're on a flat surface, okay? And you can see all the different forces you have. So, what can you solve for here? I like to try to solve for things where you don't have to do any work, all right? If you see here, this is F of G. We have the gravitational force is 60 newtons. Well, if I'm on a flat surface, what will the normal force equal? We know that these forces must be equal to each other. The normal force will be 60 newtons because if the gravitational force is pushing down on the surface must be pushing back up equally. Okay? All right, where can I go from there? I think the next easiest thing would maybe be the mass. I mean, again, it's your choice. You can solve for net force, but I'm going to go this way. I'm going to solve for the mass. The mass, I use the weight, F of G, okay, which is also the weight. Again, use either of those symbols. So that equals 60. 60 equals m times g, all right? That means it's m times 10. Again, we use 10. Divide by 10. Mass of this is 6 kilograms. Mass is 6 kilograms. Okay? All right, what else can I solve for? All right? I'm going to keep going down this list. I'm going to solve for mu. Okay, I'm going to solve for mu. Again, we did that last unit. Mu is frictional force over the normal force, which I have both. It's 10 divided by 60. 10 divided by 60. I think that's what, 0.18? Just confirming. Oh no, 0.17. Terrible fractions. 0.17. So your mu is 0.17. Okay. Now acceleration, I can't solve for that. Acceleration has to be related to the net force. Okay. I know what my mass is, but I need the net force. So this is where I've had some people get confused and they go, I don't know where to go. It's mass times acceleration. Look, okay, this object is accelerating to the right. That means there's a greater force. There's an unbalanced force left and right. There's a greater applied force than frictional force. So my net force will be applied minus friction. And I mean, I know you could just do this in your head. 50 minus 10 is 40 newtons. Okay? 40 newtons is your net force. Once you know that, now you can solve for A. 40 equals 6 times A. A equals 6.7 kilograms. Okay? So again, the main idea here, pretty introductory in terms of what I'm looking for in this particular video, that you'll just simply understand how to try to calculate a net force. And again, obviously the problems are going to get more and more complicated. We're going to do one more real quick. All right, let's look at this one. Okay, this one doesn't have as much information. You have to kind of fill it in yourself. A rightward force is applied to a 6 kilogram object to move it across a rough surface at constant velocity. All right, that is key. All right, that's the thing, is when we start doing these dynamic problems, we're going to mix in equilibrium problems so you know when it is a dynamic accelerated problem versus one that is not. So that is extremely important to pick up. Those words are so important throughout the year to catch. Okay? So it's moving at a constant velocity. The object encounters a 50 Newton of frictional force. Use the diagram to the right to determine the gravitational force, everything else basically. So let's fill in what we know. I know it's 6 kilograms. I know the frictional force is 15. If I'm going to constant velocity, that means my acceleration is 0 meters per second squared, and my net force is 0. The only way to go at constant velocity is to have no net force. So this is back to an equilibrium problem. All right, this one is pretty simple. I mean, once you catch on to that, this is going to go pretty quickly. Okay? If it is 0 net force, that means all forces in all directions must be equal to the opposite force. So 15 newtons to the left means there's 15 newtons of applied force to the right. All right. Gravitational force, I'm going to kind of speed this up. 6 times 10 is 60 newtons. That means the normal force is 60 newtons because I'm on a flat surface. All right. Again, make sure, like we practice in the equilibrium unit, be aware, when will the normal force be the same as weight? When will it not? When you're on a flat surface and you're not pushing down or up, the object's gravitational force and normal force are equal to each other. All I have left is mu. Mu will be 15 divided by 60, frictional force over normal, so 0.25. Okay? So that's just a very basic introduction to net force problems where, again, be aware the problem might be, you might have to approach it differently. We just have to remember especially that the net force is not just ma, but also the sum of the forces in a particular direction. Again, you never saw me interact normal and applied. That's because they are perpendicular to each other. Like we learned back in projectile motion, basically the x and y directions do not interact, do not affect each other. Okay, they basically create their own separate motions, which then we can look at the whole process and see how obviously that all overall looks. Okay, this object though is only moving left and right. All right, real quickly with third law problems again. And again, it's possible that I already went over this in another unit, but I'm going to just mention it again. The idea of Newton's third law, okay, is that every action has an equal opposite reaction. Okay? But I know these are confusing. These cause a lot of confusion. Okay? What we are saying is, again, with this, that force comes in pairs. Okay? Force comes in pairs. All right. When we went, again, I don't know whether this is talked about already, but it's probably good just to talk about it again. Weight, gravitational force. Okay. Weight is a force pair between the object and the earth. All right. The earth is pulling on the object is pulling on the earth. The normal force is between the object and the surface. Okay? Object and the surface. All right? Friction, these are usually the common ones, is also between object and surface. Okay? But one of the biggest things I know people make a mistake on is they think the weight and the normal are force pairs. Okay? These are not force pairs. Even if they happen to be equal to each other, they are not force pairs. All right? So for example, right, if I have an object, say it's a 2 kilogram object sitting on a table, on the earth, okay? We know if I say draw the free body diagram, I have weight down and normal up, okay? The weight would be 20 newtons, the normal would be 20 newtons because the object is at rest, it's sitting on the table. Does that mean the weight is paired with the normal? No, okay? They are not paired together, all right? What is creating the weight? The weight is between object and earth. The normal is basically, I mean, obviously it is reacting to that, but it's not the force pairing. This is between the object and the surface. All right? They are two separate force pairings. All right? Obviously, yes, without the weight, we wouldn't have the normal force. I understand that. Okay? But the idea is, when I say what's creating the weight or what's creating the normal, let's do it that way. What's creating the normal? Not the weight. Not the weight. Okay? The normal is created because this object is happening to push down on the object. Why is it pushing down? I don't care. Okay? It obviously is something else related to it. It's the earth. All right? But then the idea is the surface must push back up. We have that force pairing. Okay? So a classic example that I obviously do in the classroom all the time is, pushing that cart. Okay? So if I'm pushing my big desk, okay, pushing the desk across the floor, why does it start moving? Because everybody asks me that. They go, well, okay, if you push against the desk with 20 newtons, doesn't it push back against you 20 newtons? Doesn't that mean it shouldn't move? That's a very good point. Very, very good point, but that's not correct. Okay? What they're looking at is, this is definitely true. If I push against the desk 20 newtons, it's pushing me back 20 newtons. The thing is, the frictional force between the surface and the wheels, maybe the frictional force can only push 15 newtons, which means the wheel pushes the floor back 15 newtons. But the idea is, since my applied force is greater than my frictional force, all right, because I'm not pushing against the surface, the wheels are pushing against the surface. Because the applied is greater than the frictional, the object will start moving. In this case, it will actually start accelerating. Okay, so that's where we're going to be able to keep practicing these problems. And again, just keep asking questions about them. You will be fine. But again, look, you got to be focusing on like each force. Each force is its own pair of interactions. Okay? These are not force pairs. All right? Each individual force on a free body diagram is not a force pair with something else. They can happen to be equal, but they don't have to be because they are interacting with different substances, different surfaces. All right? So that's it. Thank you.